Hi, I'm Danilo, and I'll be talking about generative models. So, as we have seen before, we talk about the different approaches to representation learning. Some involve generative models, some don't. And here we'll focus on a unifying perspective of various generative models that have been used for representation learning over the several last years. We can think in terms of a taxonomy of generative models represented by this tree highlighted at the top of the slide. And this tree roughly categorizes models as directed or undirected, as implicit or explicit, or as being latent variable models or exact likelihood-based models. And we will expand every branch of this tree in the follow-up slides. But first, when we talk about generative models in machine learning, we are really talking about three things combined. The first thing is the generative process itself, which is what we traditionally would call the generative model in statistics. But we also group together the model with the learning principle, which is the thing we're going to optimize to make the model solve the task that we wanted to solve. And in general, we cannot directly approximate the we cannot directly use the learning principle that we choose. We have to resort to some kind of approximation. So we cannot really disentangle the model from the learning principle from the approximation that's used, because these three things have to be chosen together in practice. Now let's see in more details this taxonomy of generative models. At the very top, we have these two major classes, which are undirected and directed models. Undirected models are what some people call energy-based models as well. So they are just models that prescribe a unnormalized likelihood function on observed data, but there is no prescribed mechanism for sampling from this density. So you have to resort to external algorithms and approximations to do that. Directed models, they prescribe both a likelihood and a mechanism of sampling in a causal way. They prescribe a order in which you have to sample the variables. And directed models can be further broken down into two major classes: explicit and implicit models. Implicit models are models that provide a sampling mechanism, but do not have an explicit or cheaply computable likelihood function. Explicit models, on the other hand, they provide both a sampling mechanism and the likelihood function. And you can further break this class into two kinds of models. First, models with exact likelihood, which direct attribute likelihood to the data. And another class of models, they attribute likelihood jointly to the data and some unobserved variables. And in general, these models also require some approximation to train. Obviously, implicit models can only be trained with approximate algorithms. So, and at the bottom, I provide a few examples of models that live in each of these branches. We can represent all these models into graphs, which express relationships between random variables. So in these plots, random variables are represented by circles, and the dependency structure is given by these arrows and lines. So we have autoregressive models at the top and factor graphs at the top right. And at the bottom, we have a simple representation of latent variable models. On the bottom left, you have explicit latent variable model, and on the right, it's the notation for an implicit latent variable model, where the circle, you can note the missing circle, the variable x at the bottom, which indicates that there's no likelihood function there. Now, we will focus first on directed models, but we will focus mostly on directed models, but a lot of the things we'll discuss in this next slides are generically applicable to any generative model. And we will then go back to undirected models in the end. First of all, what does it mean to learn a model or train or fit a model? So generative models, they define either explicitly or implicitly a probability density. Probability density is a function that tell us how concentrated the data is in different regions of space. And what does it mean to fit in light of this? It means that we want to approach the density function defined by the model by the density of the data, according to some measure of mismatch between these two densities. This measure of mismatch between densities is what we call a probability divergence, which is simply a functional that takes two divergences and outputs a non-negative number. And it outputs 0 if both divergences are exactly the same. So once you have decided which divergence we want to use, we should start setting an optimizer that will try to minimize this divergence. On practice, though, there are infinitely many divergences we can use. And the challenge is how to choose between them, because each one of them will emphasize a different aspect of how the model should match the target density. And this is particularly important under the assumption that the models are not perfect, which is the most reasonable assumption we can make. As an example, here, imagine that you have this bimodal target density shown by the black curve, and the model can only produce a single mode, so it's a Gaussian-like model. By minimizing each various different divergences, you can still get different answers. So which answer you want, it's really up to you, depend what kind of task you want this model to be useful for. So this is a design choice that's also part of the model, and it cannot be made in advance in a principled way. It's really a situation-dependent choice. Now, most of the vast majority of publications in generative models focus on one particular family of divergence, which we call the F divergences. So F divergences are defined on the left side of this formula, and there is a very nice result which relates the F divergences to another type of divergence, which we call the integral probability matrix on the right. So what this formula means is that we can bound the expression on the left by the expression on the right by choosing a suitable test function phi, and calculate difference in expectations under the target density and under the model. The reason why this formula is so interesting is because F divergences are practically impossible to use, simply because they require the knowledge of the density of the target data. But on the right, all we need are samples from the target. We can see that the only term involving the target density is the expectation of this test function phi under the data. So that makes it very convenient in practice, because now all we need is to sample from the data. Moreover, the same thing happens with the model. On the left, we have to know the density of the model Q. And on the right, we don't. All we need is to sample from the model. This is the key idea that allowed Gantt's model to flourish and become so popular. is that this simple relation allows us to train these models just using samples and not using explicit likelihood functions. As I said, this theorem relates F divergences to integral probability metrics via this upper bound. And there are various integral probability metrics that are known and used in various GAN publications. When we put everything together, we can now write our final objective to solve, which is we still want to minimize the divergence between the target density defined by the data and the model. So we want to minimize this density with respect to the model Q. But the expression of the F divergence in terms of integral probability metrics measures provide us an upper bound, provide us a lower bound on F divergences. So we have to maximize this lower bound first. So the resulting problem is the saddle point where, so that results in a saddle point which now we have to solve with our optimizers. And the fact that this is a saddle point makes it very hard for this to work in practice, but a huge amount of progress, both theoretical and heuristic trial and error based algorithms have improved a lot our ability to solve this kind of min-max problem to make GANs work. For a particular choice of F in F divergences, we can have both a lower bound on F divergence and an upper bound on F divergence. And this upper bound is what we call the negative elbow, up to a constant. The difference between the IPM integral probability measure bound to the F divergence and the elbow is that the elbow is a convex function of the model in function space. So there's no saddle point, there's no min-max optimization. It's just a min-min problem to solve. This makes optimization much easier, but under the constraint that the elbow requires explicit knowledge of the likelihood of the model. So as I said, examples of on both sides of these inequalities for F divergences are GANs and VAs. Various GANs that have been published over the years, they are just they have different formulations and written in terms of different losses, but they can most of them can be mapped back to the F divergences, as I said, and this paper provides a dictionary of the F functions that explain various different versions of GANs. Okay, now that we gave a general overview of VAs and GANs and generative models and probability divergences, let's expand a bit on the VA models. So, as I said, the VAs are explicit models with latent variables, and there's a huge literature in this family of models, which I will not expand in details, but we will focus on a simple aspect of VAs now. Okay. So before we dig into any of the training details of a VA, I just wanted to do a little bit of a translation here. So in the first part of this talk, Ali talked about autoencoders, and he used graphs like the one on the left here. So these graphs are computational graphs. So this graphs is how we implement the model in the computer. But in terms of as a generative model and that defines a probability density, we use the representation on the right that contains both that explicitly have the separation between latent variables, observed variables, and an inference mechanism. In practice, when you put all these things together to actually train the model, the computational graph that will result from the variational approximation that we will discuss in a bit looks like the graph on the left. So now expanding a bit the math of this graph, we want to compute its likelihood, but because there are latent variables, we have to solve to marginalize them out, and for any interesting kind of model, we cannot do this integral exactly. So in practice, what we do is to introduce a test density, which is easy to sample from, which is also called proposal or encoder or variational posterior model, and apply a inequality based on the concavity of the log function to derive a lower bound on the likelihood. Again, this is just a derivation of this bound I showed a few slides ago on F divergences. This variational bound can be understood in terms of two terms that have a very clean interpretation. The first term is what we call the reconstruction term, or in information theory, it is distortion term, and another KL divergence term between the approximate posterior or encoder and the prior of the model, which is a form of regularization or a rate term in information theory. So now we have a tractable objective function for this model, which is called the elbow, evidence lower bound. On practice, when you put everything together, that's how the problem looks like. As I said, once we put the approximate inference together with the generative model, the resulting computational graph looks like the graph on the left. A very simple instantiation of this model was given the two papers above, and they are defined as having a simple spherical Gaussian at the top and a neural network that takes that Gaussian and transforms it into an image. Okay, so talking about GANs. Before we start, I would like to write the likelihood of a GAN in the same way as we did for the VA. So when you do that, we see that we start seeing better why they're not so different. The formula, as we show here on the right, is almost the same as in the VA slide, with the difference that you have this delta function instead of a smooth P of x given Z density. So as a generative model, that's really the only difference between the two families of models. But GANs can also be seen from a different perspective. So at least the algorithm that is used to train GANs can be seen from the perspective of estimating probability ratios between the model density and the target density without knowing the probability densities explicitly. So how do you estimate the probability ratio without explicitly computing the densities? Well, it's known that a classifier should do exactly that. So a classifier that's training to distinguish samples between model density and data density should learn exactly the probability ratio between the two densities, if optimization works. Based on that, we can build a new loss, which is based on the heuristic that a generative model that is good should be able to fool the discriminator, in the sense that the discriminator should not be able to tell the difference between samples from the model and the data. And this leads to this loss in the middle there. And now that results into a min-max kind of objective function there. So as I said, so this is a different perspective in how to derive this loss. But at the beginning of the slide, they provide a much more general perspective that where this kind of which generalizes completely this view of interpreting a GAN in terms of lower bounds to F divergences. Okay, we have covered VAs and GANs, and let's talk about energy-based models or undirected models. So these models are defined by some energy function. There is also a enormous literature on that. The main idea is to try to solve the task implicitly via optimization. So the model defines the energy, and the answer to the task that we want to solve is some minimum of this energy. So this is one view of the problem, which is illustrated in this slide. Here we have a pair of image X and the label Y, and we build a joint energy between these two quantities. And the decision of the model is the label that minimizes this energy. So that's one way of thinking about energy-based models, is a kind of implicit way of defining the answer of a machine learning system. Again, these slides are just illustrating what should happen to the energy landscape as you optimize this. The idea is that the energy should grow everywhere except where the data is, except where the manifold of the data is, where the energy should go down. So it forms a valley with the minimum at the correct answer. This is just illustrating the same thing, but with more emphasis on the landscape of energy. But now the challenges of learning this energy function. So if you try to write the log likelihood, explicit likelihood of a energy-based model, it will look like the form at the top of this slide. So it's just some x of minus the energy. The issue is that we don't know how to normalize this density. So we have to compute the normalizer in some way. This normalizer is the integral of this exponential, and it can be very hard to approximate this integral in practice. So if you try to compute the gradient of the log likelihood of such model, you get this formula at the bottom. So the first term is very easy. It's just the gradient of the energy computed at the data. So this is very cheap, relatively speaking. But the second term is the thing that is hard to compute. It's the expectation of the gradient of the energy under the model itself. So on practice, the only way you can to approximate this is by producing samples from the model. But as an implicit model, as a energy-based model, we don't know how to sample from this model cheaply. So there are many things we can do. Before going to alternative algorithm, I'll go through various ways we can use to sample from this model. So one of the simplest things we can do is called the Langevin sampler. So this is very popular in machine learning papers because of its simplicity. Langevin sampler is merely a gradient, a descent algorithm with noise. But the nice thing is that we can prove that such a simple sampler will converge to a sample from the target density if you wait long enough. On practice, because we have to discretize time, this guarantee is lost and it becomes approximate. But there is a way to correct that with a acceptance rejection-based algorithm, which sees the Langevin samples as just proposals, which are then accepted or rejected with some probability given by this formula. And the paper indicated above provides the optimal value of this acceptance rate that we should tune the algorithm to achieve. An alternative algorithm to sample from an energy-based model is a Hamiltonian Monte Carlo sampler, which is a different with a different way of interpreting the target density by augmenting the space with a momentum variable and adding an extra energy term for this momentum variable and following the Hamiltonian dynamics. So the algorithm is also pretty straightforward to implement. We sample initial momenta from a Gaussian and then evolve the momenta according to the Hamilton equations of motion indicated above. And in continuous time, it is also guaranteed that the marginal distribution over the position x will match the target density. Again, the same thing that happens with the Langevin sampler. On the computer, we have to discretize time, and that introduces an error of the sampler. And the way to fix that is with an acceptance probability, which is calculated in the formula below. Okay, so now we have explained that if you want to maximize the likelihood of energy-based model, we have to, if you want to do this explicitly, we need to compute a term which involves a sampling from the model, and we expanded two algorithms to produce such samples. But this whole strategy is quite expensive. We need to produce fresh samples for each gradient update of the model. This is very expensive procedure. However, we can think about a different divergence that doesn't explicitly involves maximizing the likelihood of the model, but using a different way of matching the density defined by the model to the data. And this can be done via what's called moment matching. And the moment matching is merely trying to get the gradients of the density with respect to the data to be equal for both model and the data. And you can easily convince yourself that if this is achieved by the model, then the probability density of the model is proportional to the density of the data. The nice thing about this objective function is that it doesn't require explicit samples from the model, and it can be calculated only using samples from the data. So that's a really good property of this loss function. The tricky bit of using this is that it involves the trace of the hashing of the model, of the likelihood of the model, which in many problems is prohibitively expensive. But there are also tricks to reduce the cost of that via a stratified sampling. So this algorithm has shown very promising results recently as well. Now I will let Irina take over the different levels of modeling. Thank you very much.
In the second part of this section, we will look over our model zoo through a different perspective. First, we will consider manifolds and how thinking about their topology may help us troubleshoot the existing representation learning methods and develop new ones. Then we will look at the differences between modeling data using statistical, causal, or physical methods. Let's start by thinking about manifolds. Many of you probably have heard of the manifold hypothesis that underlies a lot of what we do in machine learning. The manifold hypothesis suggests that real-world, high-dimensional data lie on low-dimensional manifolds embedded in the high-dimensional space. Let's unpack that. Let's imagine that our data consists of images of a 3D dragon shape, taken with a fixed camera, but under different lighting conditions, where the source of light moves on a sphere around the dragon. In the pixel space, this data will form an n-by-n manifold. However, since we know how the data was generated, we know that we can also represent it using a significantly lower dimensional manifold of a 2-sphere embedded in a 3-dimensional space. Taking this even further, some of us might want to go ahead and compress the representation into a 2-dimensional Euclidean space by projecting the sphere on a 2D plane. Indeed, There are many working examples of useful 2D projections of a two-sphere, geographical maps for once. However, any scholar of projectile geometry will point out that such projections will create distortions in size, angles, distances, or directions. Different projections will preserve different properties, but no projection can preserve everything. Hence, the main point I will try to make in this part of the talk is that finding the right low-dimensional manifold for our high-dimensional data is something that is worth thinking about in more detail, because when it is not done carefully, we can end up in a situation where the topology of the true data manifold is disrupted in a way that can be problematic. In order to start thinking more about manifolds when designing our models, let's understand them better by introducing some basic notation from differential geometry. A manifold is a topological space that locally resembles a Euclidean space. Let's look at the circle, one of the simplest manifolds. If we zoom in on an infinitesimal piece of the circle, it will look like a straight line. Furthermore, we can find a continuous and invertible mapping or a homeomorphism from a segment of the circle, for example the yellow arc, to an open interval on a line, in this case from -1 to 1. Such functions are called charts. The set of all charts that cover the whole manifold is called an atlas. These concepts should be pretty familiar intuitively if you have ever heard a geographic atlas of the world in your hands, which should also typically be made up of many pages or charts that are flat 2D projections of the different regions of the world. When we move between different pages of the geographical atlas, we know how they correspond to each other because of the small overlaps that exist between them. The same thing allows us to move between the different charts of a manifold. For example, to move from the top chart to the right one, we can use the composition of the inverse of chi top and chi right. The resulting function is called a transition map. Note that for each manifold, we can come up with many different choices for charts, atlases, and transition functions. Here is an example of a different atlas for the circle that consists of 2 charts rather than 4. Manifold need not be connected or closed, as demonstrated in these 4 examples of 1D manifolds. Here, each manifold is indicated by its own color. Not connected manifolds consists of a union of multiple disjoint non-empty sets, like the red, blue, or green examples. Manifolds that are not closed extend to infinity, like the open-ended parabola or hyperbola. These manifolds are 1D because locally each of these manifolds resemble a 1D line. The H-shaped form on the right is not a manifold, since at the point where the 2 circles meet, it is impossible to find an invertible smooth mapping to a line. Here are some examples of 2D manifold. Each one locally resembles a 2D plane. It is important to note here that the Euclidean space is also a manifold, but it is a manifold where the atlas contains a single chart, and this chart is just the identity function. We can measure distances, angles, and areas easily using inner products and other well-known tools from Euclidean geometry. The Euclidean space is the one where our intuitions hold and calculations are easy, so we strive to operate in such flat, simple manifolds. Unfortunately, real-world data often lives on more complicated, curved manifolds, where these intuitions break down. On curved manifolds, distances cannot be measured with straight lines. The sum of all angles in the triangle is not equal to 180 degrees, and the ratio of the circle's circumference to its diameter is not equal to pi. The implications of this is that many properties that we may desire to unlock by learning representations may not work on curved manifolds. For example, the parallelogram model of analogy making, like inferring that the relationship from king to queen is the same as the relationship from man to woman, popularized by word-to-vec embeddings, breaks, when it is applied over curved manifolds, like the manifold of 3D rotations. So how do we calculate distances, or geodesics, when talking about curved spaces on curved manifolds? To give you a flavor of the complexity of the task, we first need to introduce the notion of tangent spaces. Let's imagine we have an n-dimensional manifold M with a chart phi. Let's also imagine that there is a curve that traces a path on the manifold parametrized by a function gamma of t, and which passes through a point x when t is equal to t0. Any point on this curve can be represented in Rn by projecting it through our chart phi. Now imagine that an ant is crawling on the manifold along the path gamma. Its velocity at point x will be the vector v, which is the derivative of p with respect to t at t equals 0. Note that since p is in Rn, the velocity vector will also be in Rn. V is called a tangent vector at point x. Now, gamma t is just one of the possible paths on the manifold that passes through the point x. There can be many possible such paths. The collection of all possible tangent vectors obtained from all possible paths that go through the point x on the manifold makes up the tangent space at point x. The reason why we care about tangent spaces is because we need them to define a Riemannian metric used to measure distances on smooth, curved manifolds. A Riemannian metric is a family of functions g that take in two tangent vectors at the same point x on the manifold and outputs a real number that measures the distance between the tangent vectors. This distance will change smoothly as the point x is smoothly translated on the manifold. The Riemannian metric is the generalization of the inner product that we are familiar with on Euclidean manifolds, but with the additional term that corrects for the distortions introduced by the non-zero curvature of the manifold. One way to calculate this correction term is by taking the product of Jacobians of the function q that maps points from the tangent space to the high-dimensional Euclidean embedding space. Given that the manifold curvature may be different at every point, the tangent space will also be different, and so will the metric. Hence, while on flat Euclidean manifolds the metric is identity, if we want to calculate distances on a curved manifold, we need to know the full tensor field of the Riemannian metric at every possible point on the manifold. This leads to two options when it comes to building models. We either stay on the original data manifold and try to learn its metric, or instead we try to learn a projection to a Euclidean manifold where the metric is simple. As you may imagine, staying in the original manifold is hard. Some of the earliest unsupervised learning methods for dimensionality reduction and clustering, like PCA, were operating on the original data manifold. These methods could broadly be described as performing two steps. First, the data similarity matrix would be calculated. Then, a form of spectral decomposition or a softer embedding optimization objective would be applied. As we have just seen, the first step is the crucial one. Most of the methods use naive Euclidean-based metrics, which work well if the data manifold is curvature-free, but in the majority of cases, it is not. For example, when applied to the curved 2D Swiss roll manifold, these methods fail. In order to improve the situation, two directions were proposed. Kernel methods attempted to implicitly estimate the potentially complex similarity metric between data points without having to learn the metric explicitly, while spectral approaches introduced an extra step of building a nearest neighbor graph to estimate the topology of the manifold, and then performed the final spectral decomposition steps over the graph Laplacian. While these steps helped, they were still not perfect. Given how hard working in the original data manifold space is, there isn't a great number of approaches that attempt to do so. However, one recent paper is worth pointing out. In this work, Fao et al. Tried to discover disentangled manifold factorizations using ideas from differential geometry. As you may remember from Alice's section, disentangled representation learning attempts to find an interpretable factorized representation of the data. While virtually all approaches to disentangled representation learning attempt to learn a mapping from the original data manifold to a Euclidean-like low-dimensional space, this work aims to find meaningful factorizations in the original manifold space. The intuition is that meaningful transformations would commute with each other even on a complex curved data manifold, because this manifold can be decomposed into a product of simpler manifolds. For example, a torus decomposes into a product of two one-spheres. Fao et al. Then use ideas from differential geometry to discover such manifold factorizations. The main idea is that if you take a basis set of tangent vectors and walk them around a loop on a curved manifold, this is called parallel transport, these vectors would get distorted to different degrees. Those basis vectors that would get distorted through parallel transport would belong to the tangent space of the manifold we walked on, while those vectors that remain unaffected by the walk would belong to the tangent space of other manifolds that make up the product. Fao and colleagues were able to demonstrate that this method could discover the correct number of submanifolds that make up the product, as demonstrated by the red vertical lines in the figure, and recover their tangent space as well, even for products of up to 5 manifolds. While this work is only a first step towards developing a useful disentangling method that preserves the topology of the original data manifold, it opens up an exciting novel research direction. As we have seen, working in the original data manifold is hard. Hence, the majority of representation learning approaches, and in fact, every algorithm described by Ali in the second section of this tutorial, belongs to the second group of approaches that try to learn a projection to a Euclidean space, whether explicitly or implicitly. When it comes to contrastive learning, which, as we saw from Danilo's talk, is an instantiation of energy models, and is sometimes also referred to as metric learning, the loss that shapes the representations typically relies on a calculation of similarity between pairs of embeddings. While this similarity function can be defined to be arbitrarily complex, in practice, most methods use simple distance metrics, like the L2, cosine similarity, or dot product. All of these implicitly assume that they are operating on Euclidean vector spaces. In adversarial learning, the generator learns a map from the low-dimensional representation manifold to the high-dimensional pixel space manifold. The prior over the representation space is often chosen in a way that assumes a Euclidean manifold. Assuming Euclidean topology of the representation space can, however, lead to problems when the topology of the true data manifold cannot be smoothly mapped to it. For example, in the case of the spherical manifold of 3D rotations. This results in unnatural jumps and distortions when we try to visualize a walk on the representation manifold, as was pointed out in the case of GANs by Tucker-Cohen. Autoencoder architectures don't necessarily put strong constraints on the nature of the learned latent manifold. However, this still often results in undesirable behaviors. For example, in an experiment described by Waters et al., the underlying data manifold was actually Euclidean, sampled from the product of uniform distributions of horizontal and vertical positions on a single sprite. In order to visualize the learned manifold, the authors took images corresponding to a grid of points on the true data manifold and projected them into the latent space using the trained encoder. We see that the VAE encoder learned the mapping from a Euclidean input manifold to a non-Euclidean representation manifold. On the other hand, the implicit regularization within the factor VAE model with the same architecture as the VAE, but optimized for disentangling, was able to recover the original manifold topology well. To conclude, thinking about the topology of the original data manifold and the explicit or implicit restrictions on the topology of the learned representation manifold may help troubleshoot problems with the existing representation learning approaches and help develop better methods. Now, let's turn our attention to the different levels of modeling. So far, all the models Ali and Danilo have talked about were examples of statistical learning. Statistical learning is what machine learning excels at. The assumption is that the data is observational and presented IID, and the models extract the statistical dependencies between the different variables present in the data. This is the weakest form of relationship that can be extracted, since it has no directionality. We don't know what causes what. We just know that certain correlations exist. We also can't do counterfactuals or any other interventions on the learned representation, which might be useful for many downstream tasks. Furthermore, as is argued by Bernard Scholkopf in his great paper linked above, the IID assumption is quite restrictive and may be the cause for many known vulnerabilities of the modern machine learning methods. For example, problems with generalization or susceptibility to adversarial attacks may be caused by inputs that break the IID assumptions. One way to deal with these problems is by moving to the higher, so speaking, modeling level afforded by the causal methods, which discover directional causal dependencies between the data variables and are capable of capturing more information alongside the statistical dependencies. Sometimes we may also want to model our data at the highest physical modeling level, implemented through a system of coupled differential equations. Such a model provides the full description of the system, since it allows us to predict any future state, extract statistical dependencies among the variables, and calculate the effect of causal interventions. Unsurprisingly, as we move up the different levels of modeling, the learning problem becomes harder. Indeed, up until recently, the physical level of modeling required human physicists to handcraft the differential equations. Recently, however, a number of models have been proposed that are starting to be able to learn such physical models from data. For example, the recent Hamiltonian generative network can be seen as a variational autoencoder with a recurrent core inside. However, instead of a discrete RNN, the recurrent dynamics are modeled using a learned system of ordinary differential equations called the Hamiltonian equations. The Hamiltonian formalism is one of the generalizations of Newton's laws of motion. In this framework, the dynamics of the system are described in something called the phase space, which is a set of position and their corresponding momentum coordinates. When visualized in phase space, Hamiltonian dynamics trace out trajectories that never cross their own path. A Hamiltonian is a function from the phase space to a scalar that represents the energy of the system. The continual dynamics are modeled by taking the partial derivatives of the Hamiltonian with respect to position or momentum. So, to calculate the next position, we use the derivative with respect to the momentum, and to calculate the next momentum, we use the negative derivative with respect to the position. The equations on the slide are presented with the Euler integrator for simplicity. In practice, more advanced integrators are used. Since HGN can learn the dynamics at the physical level by discovering the Hamiltonian equations governing the time evolution of the data, it can do more than the usual statistical generative models. Not only can it produce plausible samples and reconstruct the given dynamics, it can also roll out the system infinitely forward and backward in time, do jumpy rollouts by varying the integration time step at test time, and the dynamics are guaranteed to respect a relevant set of symmetries. As a side note, the HGN work also connects back to the manifold hypothesis by augmenting it. Not only are natural images thought to lie on a low-dimensional manifold, but natural image sequences are also thought to correspond to motion governed by abstract Hamiltonian dynamics, thus further constraining the nature of the manifold. Going back to the different levels of modeling, we can further understand the implications of their differences using the example of disentangled representation learning. As Ali has mentioned in his talk, the statistical perspective to disentangling sees it as the problem of modeling the joint distribution of pixel observations X and an assumed ground truth factorized interpretable latent distribution Z. However, assuming that the only observable is the distribution P of X, where the latents Z are marginalized out, we end up with a pessimistic result. As was articulated in the work by Locatello and colleagues, learning disentangled representations in a purely unsupervised setting with no further inductive biases and assumptions on the data or models should be theoretically impossible. As stated in their Theorem 1, we can take any disentangled factorized representation Z and find a mapping F such that the new representation is still factorized and the observable marginal distribution of the data is still the same, but the new representation F of Z is completely entangled with respect to the original factorization Z. Hence, the ground truth disentangled representation is not identifiable. The reason why the many existing statistical models for unsupervised disentangled representation learning, like BTVE and other VAE-based models, work in practice is because of the implicit biases present in the data and its interactions with the optimization dynamics, as was explained more technically by Rolinek et al. And more intuitively by Burgess et al. In the papers linked. So, if statistical unsupervised disentangled representation learning is brittle, can a causal view on disentangling help? First, let's formally introduce structural causal models, or SCMs. In an SCM, each observable random variable can be expressed as a deterministic function of its parents in a directly acyclic graph and independent source of noise. Given an SCM, we can go back to a statistical model by recovering the conditional probabilities of children conditioned on their parents. The nice thing about SCMs is that they automatically factorize into independent causal mechanisms. What this means is that in an SCM, intervening on one of the causal mechanisms does not affect other mechanisms, and knowing about other mechanisms does not inform about the given mechanisms. Note that because of the structure of SCMs, independence of mechanisms is a notion of independence between functions and not of random variables. These considerations naturally lead to a causal definition of disentangling. We assume a causal model for observations X with the generative factors G, where the generative factors can be influenced by confounders C. If the resulting model can be described as an SCM of the form shown, where G's are a deterministic function of the parent confounders and independent sources of noise, and X's are a deterministic function of parent generative factors and independent sources of noise, then we have a disentangled causal model. The causal view of disentangling matches the statistical view through properties C, D, and E that I will not go into. But it also has nice properties over the statistical model. First, the causal mechanism P of X given G is invariant to the changes in distribution of G. This means that the learned model should be more robust to covariate shifts, for example, to novel examples of color and shape combinations never experienced during training, as long as the underlying causal mechanisms are learned correctly. Second, it allows for groups of latent causes G to be dependent, unlike the statistical model that limits the modeling power of the models by assuming that each generative factor has to be modeled by a single independent latent variable. While the causal definition of disentangling is still relatively new, and hence building robust and scalable models based on this perspective is ongoing work, the causal definition has produced a nice disentanglement metric that is more reflective of the intuitions about disentanglement than metrics based on the statistical view. Here, two models are shown that were scored similarly highly by the statistical disentanglement metrics. But as you can see, they are scored differently by the causal metric. In the top row, as we change the value of position y generative factor in the rightmost subplot, we see that the values of the other learned latents that represent changes in position x, orientation, scale, or shape remain relatively invariant. So this model scores highly using the causal disentanglement metric and matches our intuitions for what disentangled representations should look like. On the other hand, changes to scale in the second row result in significant changes to the other latents of the model, indicating that this representation isn't well disentangled intuitively, and it is also scored low by the causal metric. Moving on to the physical definition of disentangling. A vector representation is called disentangled with respect to a particular decomposition of a symmetry group into subgroups if it decomposes into independent subspaces, where each subspace is affected by the action of a single subgroup, and the actions of all other subgroups leave the subspace unaffected. Let's unpack that. Symmetries are those transformations that keep some aspect of an object unchanged. Group theory is used to talk about symmetries. Groups can be discrete, like the cyclic group, or they can be continuous, like the rotation group. For example, a cyclic group of order 3 can be used to describe the rotational symmetries of the three-legged symbol shown on the left. And the rotation group of order 3, SO3, can be used to describe rotational symmetries of a two-sphere. A group is just a set G, together with an operator that maps two elements from that set to another element in the set. These elements can be symmetry transformations, and the operator is a way to compose these transformations. The elements in the set have to be associative, there needs to be an identity element, and for each element there needs to be an inverse. That makes a group. As I said, each element in the group can be a transformation, so they need to transform something. Hence, we introduce the notion of group action. For example, if we have a group of integer addition modulo 3, it may act on a set W of equivalence classes of integers modulo 3. So, if we start in the 0th element of W and apply transformation G1, we will move to element 1. If we then apply G2, we will get back to the 0th element. Hence, G2 is the inverse of G1, and their composition, as shown in the table, results in an identity transformation. The group we described in the last slide is called a cyclic group of order 3, since it cycles over 3 elements. We can also define its subgroup. Here is a cyclic group of order 2. A subgroup needs to contain a subset of elements of the original group and still be a group. If we have two groups, we can also define their direct product. The direct product will be another group with elements that are a Cartesian product of the elements of the subgroups, and the operator will be defined component-wise. We can always recover the original two groups from their direct product by finding tuples with a single non-identity element. Now we're equipped to understand the physical definition of disentangling. Let's suppose we have a simple grid world that can be completely described by a direct product of 3 cyclic groups that act by changing the horizontal and vertical position of the sprite as well as its color. The abstract state of such a world can be described by a set W. When we apply a transformation from one of the subgroups, it changes the corresponding part of the tuple in W. Now, we assume that there is a generative process B that maps the world states into high-dimensional observations that are fed into our model. And the model implements an inference function H that learns a representation Z. We also call the composition of B and H function F. So if we can learn an equivariant map F so that we can apply a group transformation and then go through F, or first go through F and then apply the group transformation without affecting the final state of the representation. Then it will induce a disentangled representation Z. Since this definition disentangling talks about learning a representation that decomposes into independent subspaces that reflect different symmetry transformations, and physical models of dynamics like the Hamiltonian generative networks learn dynamics that respect symmetries, there is hope that the physical level of modeling may lead to better disentangled representation learning methods, although this is still an open area of research. To conclude this section, Danilo and I touched on a few different theoretical lenses that can be used to systematize the diverse model zoo of unsupervised representation learning methods, first outlined by Ali. We suggested considering how the different methods approach data density modeling, what considerations they make about the data manifold, and their chosen modeling level. Analyzing models in the light of these different lenses may be helpful in understanding the trade-offs between the different models, troubleshoot their failures, and think of possible model improvements.